Okay, so our goal today is to talk a little bit about the Biot-Savart Law. It's the BS law, and for real. And we're going to try to show you a little bit about what that equation is and how we can actually put it in the computer and code it. So let me start by just giving you a very brief, whoops, let's go to here. If you want to follow along, we're on page 152 in the workbook if you want to have that open. That said, I'm just going to do something on the whiteboard here. And the links that I gave you, basically, I'm trying to give you the short version so it's not so hard to read all those links and stuff. So information overload is a serious risk with a physics class. So I'm going to start by talking about the electric field in Coulomb's law. So there we said the electric field for a point charge was K Q over R squared in the R hat. And you may recall that we almost always coded it by changing this to R vector and this sucker down here to R cubed. And then when we were doing continuous distributions of charge, this changed from to E equals the integral of K dq in the R vector all over R squared. And I should point out for this problem, usually R was something like from the, it's R final minus R initial, which was source was initial and POI like that. Oh, whoops, sorry. So we had R was basically the final minus the initial, and we usually use the term POI in our codes earlier. Now, if you recall how we ended up coding this, this integral essentially became E total plus equals K times rod dot dq, or something like this. I'll say rod and then we had star R and then divided by mag of R star 3. Sorry, I'm running out of room there. But something like that. Remember what we did is we had some kind of loop and you would run through the ith element of a list and you would get the charge on the ith element of the list, and we would multiply by the R vector, which was something like POI minus source or something like that. Okay. And so just before we go on, maybe is this familiar or any questions about that? Okay. So keep that in mind. Okay. So that's kind of your backup. Now, what are we going to do? I'll keep this one up here for reference. The Biot-Savart law looks pretty similar, except it's got a cross product. Okay, and so it says B is equal to mu naught, which is a new constant. It's just some number. The current divided by 4 pi times the integral of this. So, and I guess what I could do is I could even stick this integral out front, because you can move constants in and out. And so the idea here is it actually looks a lot like this, because we still have the R over R cubed portion. Oh, shoot, right here I had a typo. My bad. There's an R cubed there. And so the trick is we need to figure out how to rewrite this integral in Python. Now, if it helps, mu naught is just some number. It's 4 pi times 10 to the minus 7th. Let's not worry about the units right now. We'll do that tomorrow. Okay. I is current. And this is something cool that we don't have to worry about. Current is for us, it's always going to be uniform. So we're going to have the same current at every piece of the wire that we integrate over. So in this case, mu naught is some constant. I is going to be a constant for us. It's the current in a wire segment. 4 pi is a constant. So all that stuff will just pop out like this. And so what is ds? Just like when we did forces on wires, ds is basically a smaller bit of length. I'll say tiny length in direction current flows. So whereas before we were having to do a tiny amount of charge, now our integrals are literally a straight length integration. We're integrating over the length of a wire because the current, we're going to assume current is the same everywhere in a loop of wire. We're not going to do weird branching loops. So I'm going to pause for a second. Again, charge was the source of an electric field. Current along the length of wire is the source of a magnetic field. So if you're wondering where these magnetic fields come from, we can think of them as being generated by currents. Even in a permanent magnet, like a magnet that you stick on your fridge, the current loops in there are literally orbiting electrons and spinning electrons and things. Those act like current loops. Moving charge is a current. So basically all magnetism can be thought of as being generated by currents. All electric fields can be thought of as being generated by charge. Any questions about this blue crap over here? All right. So let's see how we do. So I'm going to go into GlowScript and I'm going to start coding this up. And so let me see if I could do this with you live. So I'm going to share my screen and I want you to try and do this with me. Forget about all the notes, forget about everything but what we're doing right now. Forget about anything but what this is. Let's create a new program. So if you've got GlowScript or if you're using PyCharm or something, let's think about what we need to do. And to give you an idea, actually, I'll show you just a second here. I'm going to hide something from you and then do it. Whatever, I'll share it with you. And then I think I could do this without revealing the code. So the idea is I'll run this code. I wish, I totally wish. Trust me, I know. So here's the idea here. I don't know if you can see this thing. Yeah, for sure I did. Now look at this. Inside of here, I'm trying to model each one of these as a line segment. Whoops, let me get my annotation here. So the idea is this is a cylinder right here. Let me finish drawing it. So hopefully that shows up on your screen now. I just put a red box around one of these cylinders. And so the idea is I took a straight wire and I split it into a bunch of cylinders. The red arrow inside of it represents the current flowing through that cylinder, right? So there's current that's flowing through that cross-sectional area. Now, if I could clear that and back it off. Oops. There it goes. Sorry, it's taking a little bit of time. That big blue arrow is the magnetic field. So there's the wire on the end view. Now, if you think about this, there's a right-hand rule for this if you want to know it. It's grab that wire. So pretend you're grabbing the white wire and line up your thumb on your right hand with the direction of current. So when I do that, I notice my thumb is pointing almost out of the page. Look at which way your fingers point relative to that blue arrow. Notice the fingers on your right hand are curling in the direction of the magnetic field. And in general, this gets very tricky. So I'll do that one last time. I'm going to grab the white wire and I'm going to line up my thumb in the direction of the red arrow of current. And I notice that my fingers show me that above the wire, the magnetic field points, in this case, in this view, to the left. Now, obviously, if you go the other way, let's try this again. What if I choose a point below the wire? So when I run this one, notice the magnetic field points the other way. So try it again. Notice the current is running out of the page. So grab that wire, line up your thumb with it, and curl it around. And notice your fingers now point underneath the wire. Your fingers point to the right. And so that's the right-hand rule for checking your work if you need to know it. Great. All right. So now let's try and create this code. I know it works because I wrote it this morning in like 10 minutes. So I know you could do it. So let's make our own from scratch. And we've got this if we get in a jam. Okay. So let's go to here and let's just make a new one.
Really quick question.
Yeah, go ahead.
Was that code solving the electric field?
Magnetic.
Magnetic field. Okay. All right.
Yeah. So that blue arrow was representing the magnetic field. Let's run it one last time.
Magnetic field created by the wire?
By the current in the wire.
Okay.
Yeah.
All right, cool.
So if I run that, so notice those red arrows represent current. And what we're saying here is that if current is flowing that way in that white wire, and we add up all those little segments, whoops. Oh, what happened to it? Huh. Well, my screen went blank. Let me try going back. All right, there we go. Sorry about that. Must have hit a button by accident. So the idea is if I take all of these segments and add them up with an integral, right? If I take 1, 2, 3, blah, 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 out to 20, there's 20 segments here. In this particular case, this is x equals -10. Out here, this is going to be x equals +10. The idea is I basically took a 20 meter wire and split it up into 1 meter chunks. And when I do that, let's just leave it at that. So now the interval here, the length of one chunk, I chose to call dx, right? And so in this particular case, ds will equal dx in the I hat. Okay. So going back to what I had on the board for just a second, I don't know if you can see this, but we said there was a ds cross r vector up here on this board. Well, ds is the length of the wire segment. So that's dx is the length. And then in the direction current flows, which in this case, I think is positive I hat if I look at those arrows. So, okay. Now in Python, think what this would look like. This would be a vector, right? It's a vector. And then it would be something like dx, comma 0, comma 0, right? So in Python, that is what ds would look like. Let me pause for a second and see if you buy into that. Is everybody cool with that? And then remember, the r vectors are sneaky. I'm going to need an r vector from this one to right here. So that would be r. That would be the third r vector. There's also going to be one right here from the one next to it. And then there's going to be another one right here from the one next to it, etc. So the idea is each different wire segment is going to have a different r vector. So r changes. That's going to be the hard part, is figuring out what r is. Oops, changes. Okay, so let's try and type this up now. Or any questions while I've got that up on the screen? Okay.
Yeah, I got a question. I thought R was the direction of the current. That's not the direction of the current?
ds is in the direction of the current.
Oh, okay. So then R is just the distance between the chunk and the
POI. So R is the same as in chapter 21 and 2. It is the distance from the source of the field to the location where you wish to measure the field. So source is a charge for an electric field. Source is a current for a magnetic field. Is that good?
So in this case, the point of interest is literally where the blue arrow is?
Exactly. The POI is the point where we wish to determine the magnetic field. So right down here, this would be the location of the point of interest. So all that is we just had to pick one point in space. So that's going to be the POI. And from there, you could figure out this is the B created. So that's the B field created at the POI. Is that good?
Perfect. Thank you.
Mm-hmm. All right. So let's go ahead and take a look at this now. Let's go. Let me clear all those annotations off. Clear all my drawings. And let's start this up. Okay, and so this is going to take a little longer than 20 minutes, I guess. That's okay. If you got to go, I understand, and my apologies. So let's just go into here and get yourself a code, and let's try and make it together where we're talking and asking questions. So let me, I'm just going to create a new program, BS code. It's fun to be able to use that. Okay, so literally, this is the Biot-Savart Law. Okay, so think. Somebody you can unmute. What are some constants we're going to need? What would you do?
dx.
Okay, we're going to need a dx. What would I, there's going to be some other stuff. I would actually use
current.
dx later. Okay, so we're going to need current. We'll come up with that. What else?
Whatever the mu naught.
Yeah, that's one. And so I'm actually going to group these constants in a couple of different ways. This one, I'm going to call this mu naught, and that's equal to 4 times pi times 1e negative 7. And already, can you tell what we're going to need if we have a negative 7 in there? You're going to need a scale factor. So I'm just going to throw that in, and I think this one will work. Okay, what else? Okay, Nick's been chiming in a lot. Let's let somebody else give it a shot, Nick. So you've said good things so far. You haven't missed anything. Let me throw in a number here. Everybody, let's throw in 1 amp for the current, okay? Somebody else.
We'll need the diameter of the wire.
Okay, I'm going to let the default diameter just be 1. But you could put in a diameter. That's cool. For now, it turns out I didn't need that. So that's a good thing. What else? What other dimensions of the wire, Trey?
The length.
The length. Okay. What else?
The direction.
Okay.
Or
Okay.
I guess the,
What did I just draw at the two? I'm thinking X min and X max. That was like what I started with. A left end and a right end, right? Now, the reason I chose these first is what's the other thing that we have to choose when we're slicing this thing up? We need to know where to start, where to end. What's the other piece?
the size of the slices.
Yeah, or how about or the number of the slices, right?
Okay.
The size. So you could choose whether you want to pick DX or whatever. I chose this. So let's say we wanted to slice this into 20. Now it's easy for me to get the length. Now you don't have to do it my way. Trust me, you're all bringing up great ideas. So anybody that wants, how do I get the length from my already established constants?
Max minus the minimum.
Yep. Now, for me, this makes sense because I think about where I want the endpoints of the wire to be in my mind. If you think in the terms of the length, maybe you would specify X min and then, yeah, whatever. But so how would I get DX from this?
Divide length by n.
Let's see. That's looking pretty good. Okay, so now let me see. You know what? Remember how I pointed out on the board? Mu naught I over 4 pi shows up and it factors out all the time. To make my life easier, I called a thing constant. And I just said this is equal to mu naught times I divided by 4. Oh, whoops, 2. Whoops, it was 4. Now, this begs the question, you might notice, isn't mu naught I over 4 pi just 1e negative 7? And it is, but this just makes more sense to me when I'm organizing, right? I clearly see the current. I can clearly see that I wrote down a physics constant, right? And this is going to be the constant that I use in my integral, so I don't have to keep writing this crap all the time. Now, you don't have to do that, but yeah, that's something I recommend. And see if there's anything else I want to say about that.
Should the 4 times pi there be in parentheses?
Yeah, or that. Sorry about that. Do you agree I could divide by 4, then divide by pi is the same?
Yes.
All right, cool. All right, so that's good. And then I think, all right, so what's something else? We're going to try and calculate a magnetic field at some point. So what's another thing we need to specify?
The point we're calculating.
Exactly. From? And is that going to be a vector or a scalar? Is a position a vector or a scalar?
Scalar.
Vector. So you have to specify x, y, and z to specify a position, right? So it's a position is a vector relative to the origin. So let's just say, let's start with 3, 0, 0, okay? Or actually, no, let's do 0, 3, 0. Otherwise, the point of interest will be in our wire. Okay. All right. Let's see. What else do we have here? Let's see. We got our current. We got this. We got a scale factor. Oh, and then I'm going to go ahead and just throw this in here. Our goal is to calculate a magnetic field, right? Is a magnetic field a vector or a scalar? What do you think? Do you remember?
A vector?
Vector. So let's just put a vector and just call it 0, 0, 0. So we're just initializing that. So now the computer knows that anywhere I do a B total, it's going to be a vector. Let me make sure I got everything. Oh, yeah. Okay. Now, okay. So any ideas what you want to do next? So we've got most of our constants there, pretty much all of them. We know the length. We need to start doing this thing. And let me remind you of the calculation. I'm going to write it on the screen here, somewhere over here. So remember that B, whoops. Let me do it in the color code. So we know that B is going to equal mu naught I over 4 pi times the integral of ds cross r vector all over r the magnitude cubed. So that's what we're trying to figure out, right? Remember, an integral is essentially, in computer land, that's just a sum. Whoops. So we need to add it up over all segments of this constant. That's the mu naught I over 4 pi times ds vector cross the r vector all over r quantity there, cube there. Okay, so that's what we need to do, right? An integral is essentially a sum. When you see that we need to do a sum, what's something that jumps out in your mind? or I don't know, any thoughts about anything, any ideas?
Loop.
That's what I was looking for. We need some kind of loop. And let's see what the chat was. Yep, Bobby, I agree. Right. So we need to add something up. So let me ask you, what do you think is going to end up being cleaner, a for loop or a while loop?
For.
Probably a for loop. Okay, so let's do this. And so for x in a range, what's the lowest x value I want to use? X min, right? What's the upper limit? And then what's the interval size?
Dx.
Dx. And you need a colon and an enter. Okay. Now, before we do the magnetic field calculation, let's first draw the wire segments, right? First, help me draw the wire segments. Okay. So what shape do you want to use to split up the wire? Most wires have what shape? Cylindrical, right? So we're looking at this. I don't know if you can see this up here, right? Well, no, that's, yeah, but that's supposed to be a cylinder. All right, whatever. So let's just say, let's give our cylinder a name. I'm not going to be very creative. Actually, let's call it this, segment. So we're going to build up an entire wire out of segments. That seems like a good name, right? You can pick whatever you want. You could call it my cylinder. You could call it cyl. Okay, but cylinder. So give me, obviously, there's going to be the position. There's going to be the axis. And then I'm going to throw in one more for you. I recommend doing an opacity, at least at the beginning, of something less than 1, just so we can see inside the wire if we need to. So these are the attributes we should, and like Trey was mentioning, you could also adjust the radius of the cylinder if you wanted to make it a skinnier wire, which might be advisable depending on the dimensions. But so Trey, that's where your radius would come in. Do you agree?
Yeah.
Okay. So where is the position of the first segment in the wire? What do I, or how do I want to specify this position?
Would be X min plus Dx.
But careful. So you're right. It relates to X, right? So the first one would be at X minimum. Now, the cylinder, I happen to know if you're building a cylinder like this, the cylinder's position is not in the middle of it. The cylinder's position is at the shaded blue face on the left end, basically. So you specify, when you specify a cylinder, you tell it a face of the cylinder. So based off that, maybe it would help to remind ourselves what this for loop does. It's going to create a variable named X, and X will start at X min. It will go to X max in increments of dx. So, so what do you, was that Alan? Was that your question, Alan? Or was that your comment? Yeah. So Alan, I wouldn't say what you said. That's a good thought and you're on the right track.
No, I see that now.
Okay. So that was a good idea. Other thoughts? Or Alan, you could try again if you want.
It would be a vector.
A vector, that's for sure. So you better tell it it's a vector. So something, comma, something, comma, something.
And then x, 0, 0.
So let's think. What will this do? This is going to walk into this for loop at line 16 and say, hey, start here. So the first x value would be x, which is actually pretty close to what Alan just said. Then I'm not going to do shit in the y-axis or the z-axis. And now what's going to happen for the next one? It's going to increment by dx, and it's going to scoot over and scoot over. So I think that's going to get it done. So that was good. How about the axis? Which way do we want our cylinder to point, and how long should it be? So this dimension right here, give me a second. That dimension is the axis. For us, what is that axis length? Or what is that? And Trey got the last one, so I'll wait somebody else out. How long is that segment going to be? How long should each segment be?
dx.
How much in the y and how much in the z?
0 and 0.
So then what is this? Is it a vector or not?
Be a vector, wouldn't it?
Yep. And how long in the x? Like that, right? What do you think, people? Is that making any sense at all? What we have done is we said, draw a wire segment. The segment should be a cylinder. The left face of the cylinder should be located at some value x. The length of it should be dx, and I want it to be halfway invisible. Okay. Sweet, we're good to go on that. Now, it's getting kind of messy here. I'm gonna erase all my drawings here. Well, actually, let me just erase this bottom one. Let me see if I can select it. There we go. Look at this. Old man learns new trick. Okay. All right. So there we go. And we don't need this anymore. Okay. So generally speaking, that's going to get the job done. That's going to run the wire. I'm just going to run this really quick and see if I made any typos. Okay. You got a wire. That's it, right? So just check it one more time. There it is. You got the wire. So that's cool. Let's go in there. Any questions about that? Does anybody have any advice as to what we should do next immediately? There's something I would recommend. We made all these segments. Wouldn't it be nice if we could modify them later and do stuff with them?
Like a list?
Oh, what a good idea. What might be a good name for that list? What are we building?
I'm not sure. I just got here.
We're building a wire. Right? Oh, Ryan, so we're way late. I don't know if you noticed. So sorry,
Oh,
man.
yeah, no worries. No worries.
All
I
right.
just thought I'd pop on anyway. This is interesting. I find it fun.
Yeah, so my apologies. I always underestimate how long everything's going to take. Okay, which is true of projects in general for all of you guys as you go in your career. Projects always take too long, right? So, okay. So how do I get that segment into here? Do you remember what line of code we need to do to get the segment inside the wire list? Started with the letter A. When you add something to a list, there's that
I think
word.
it's like append.
Append, yeah. So append, and then let me make sure I had it written down here just so I didn't have to look it up. I think it's parentheses. So the idea is now we're going to put all that work into a thing called a wire, which is a list. So again, I defined the list up top. And then I'm going to add the wire. I'm going to add the segment, which is a cylinder, into the wire. So that means later on, we can use the properties of the wires to deal with this crap up here. Let me just show you. So when I start doing this calculation, I can just say wire dot position or wire dot axis and stuff like that. Okay. So far, so good. All right. Now we need to do a different loop. So I'm going to get out of this loop. Whoops. All right. And okay. So now what we want to do is we want to figure out the total magnetic field, right? So what we want to do is we want to go through, and this is saved, so I'm just going to remind you what we want to do here. So sorry that this blob here is in the middle, but the idea is, I don't want to move these annotations around and lose them. Oh my gosh, come on, computer. The idea is we need to go from this wire segment to here. Then we need to go from the next wire segment to here. And each time we have to get a new contribution. So we need to add up the contributions from each of these segments. And we see that the R vector is going to change. So clearly we need to make a new loop. And in this new loop, what do we need to do? We need to calculate the R vector and the DS vector and the cross product and the field contribution. Again, we got to do, this is just a constant, but we need to make sure we know what DS is for each segment in the loop. We need to know what the R vector is so that we can also get the magnitude. And then we need to add those to the total contribution. Got it? So let me erase some stuff really quick. Okay, and then let's go back to our code. Where was that one that we were playing with? Johnny D? BS code. Okay, so help me out. I need to do another loop. What do you think the name of the loop, or how should I open up the loop, or I don't know what you call that. What's the loop statement, the for statement? I want to do a calculation for each segment in the wire. Take a guess what the for statement is. For what in what?
For I in wireless.
I think I couldn't hear all of that, but I think you said in wire.
Yeah,
right?
yeah.
That's good. What are the objects inside of the wire called?
Segment, probably.
For a segment in the wire. So what this will do, it will go to each segment that's in the wire. Well, what's inside the wire? A bunch of cylinders. So when you say, you could say for taco in the wire, but what is really in the wire? Well, the wire is filled with segments. So why don't we use that descriptive name? So what we're trying to do is for each segment of the wire, we want to calculate the magnetic field. And now this code makes sense physically. All right. It has a min. Is that okay?
Yeah.
Nice job. Nice job. Okay. So what's the first thing we have to do?
We need to calculate the radius, the distance from the POI to the segment.
Okay. It's from source to POI. So what do I write here, Min?
It's POI minus while for each segment, so it's gonna be in parentheses I dot BOS.
Okay. And this is where now we're into a Python syntax thing. So what he's trying to do is go pick the ith element of the wire. That's right. Now, so with the way the for loop works, we've got to be careful with your syntax. And I'm just going to cheat in a little bit and look at my notes. So what did I have here? For the Python for loops, this is how it's done. You would say just segment dot pause. And so this
Oh,
it says for each segment, we chose segment, right? And so it will say, get the segment that I'm working on, which would be like the ith element in the loop. Because what this for loop does is it says, get each segment in there. So it's going to go through and it's go to the first segment and get its position. And then when it gets to the end of the loop, it'll start over and go to the second segment in the wire and do it. Is that good, Min?
Yep.
Nice. Okay. Now be careful here, people. There's going to be an error introduced. Where is the segment's position? Look on my screen. Look at the red colors.
At the bottom of the cylinder.
Yeah, and we should probably go to the middle of the cylinder so that our code converges more rapidly. So Trey, since you were crazy enough to speak up, how would I get this to the middle?
Add dx divided by 2
To which component?
to the x position.
So then how would I write it?
I
I can't just do this. That's not going to work.
You have to write it as a vector.
Yep. So I'll write it as a vector. So was that Alan? Help us out. What would I write then?
That would be the dx over 2, 0, 0.
Nice. Trey, you agree?
Yes.
Nice job, both of you. So I'm trying to make this a little bit more interactive. So whoever speaks up, I'll just pick on you. And then whoever wants to speak up, I'll switch to you guys. Okay. So we're just trying to learn and have fun and get something learned. That's all. Okay. So I appreciate the positive attitude and the collaboration, all that, blah, blah, blah. Okay. So what's next? Somebody help me out. We got the R vector. Any ideas what to do next? Look what I need. I need a DS. Any thoughts?
Would that have to be a vector as well?
Yeah. And so what is that vector? We've actually already written it.
Is it the axis?
Segment.axis. Nice. And maybe that's what you were going to say too, Alan. It looked like you hit on mute there. So
Yeah, I was scrambling to get to the button. Sorry.
no, you're good. Right? Is everybody cool with that? All right. So now, do we have all the pieces? I think we do, right? How do I calculate the B field? Let me ask you, before you do any segments, before you add, okay, each segment is going to add a contribution. We haven't done any segments yet. So what is the B field right now before you add anything?
0.
0. We already said that, right? B total is 0. But I want to add to it each contribution. I want to plus equal each segment's contribution. Does that make sense? I want to add to the previous total. So I want to plus equal. All right, somebody help me out. It's all there. Go ahead and tell me the formula.
Would it just be the equation, the mu naught I?
And do you agree that we simplified that by blobbing it into constant?
Yeah.
Nice. Okay, times what?
Times ds cross r.
Take a guess how you do a cross product in Python. What function do you think it is? What would be a good name for cross product?
Isn't it cross?
Yep. Now the arguments are first vector comma second vector. So it's ds cross r. And then what do I need to divide by?
R cubed.
Which is, how do I get r without a vector in Python?
Is it the mag?
Mag. R. Then what?
Star 3.
Star 3, right? And now, if we want to know if this is correct, how are we going to know if it's correct? Or how are we going to know what the value is? How can I make the computer do something for me? Throwing a print statement is what I was digging for. Print. Now, I happen to know a special case. So I know a certain value. I know a theoretical value. So I'm just going to cheat and tell you the theoretical value. So that's mu naught star I. And I'll actually, let's print the magnitude of it. Actually, let's not. Let's do this. So the magnitude of the field, I happen to know, we're going to learn about in class tomorrow. It's mu naught I divided by 2 divided by pi divided by the distance you are from the center of the wire or from the perpendicular bisector. More on that tomorrow, which is POI dot Y in this case. So there's our theoretical value. And I'll just do a print. Let's do the percent difference. Oh, whoops. All right, let's not. Let's run this and see what we get. We'll just look at it. All right, and so look at these numbers down here. Pretty good, right? The B field, I know from experience, that's in the correct direction. I see that the magnitude works. I could tell this code is working. All right. I could tell this code is working. So I'm going to go back and look at this code one more time and just kind of, well, I don't know, any questions? Is this code sort of making sense?
I have one question.
Go for it.
For each individual segment, did we? Oh, never mind. You know what? I see it right there. Dx divided by 2. We did go to the center of the segment. Okay.
Yeah, yeah. And if you don't do that, let's see what happens if I take this away. So let's just how about I just change that to 0, right? Now it'll still work. So let's see what it looks like if I run it this way and see if it makes a big difference. It doesn't make a huge difference. So this one was like 5 6s. And this one, when I put that in there, when I run this, let's see what the difference is. It's also 5 6s. So for this particular case, now keep in mind, however, this is where things get sneaky. Depending where the POI lines up, it could be a big difference. So what if I had done this? What if I had shifted this by like 0.3 and just shifted a little bit to the left or right? So now things might be slightly different if we ignore that dx, or maybe not. Or maybe what if we go farther away? So the idea is that dx over 2 will not make a big difference in some cases, and it may make a big difference in other cases, depending on where your point of interest lines up. Does that make sense, Nick?
Yeah, for sure.
Yeah, and it's going to be pretty, like this particular example and point that I chose has a lot of symmetry. Generally speaking, if we go from the center of the segment, we should get slightly lower percent differences on average for an arbitrary POI. Yeah. Now that's a really boring lab, but that's something you could do, is you could find the regions where the POI actually causes an error there, but whatever. All right. Other questions? All right. And so now, obviously I threw in a lot of bells and whistles and arrows and things, but that stuff is stuff you can do. But the core physics of creating the magnetic field is there. Now think about this. If you wanted to get the force on a charge, well, I know that force on a charge is equal to Q times let's just say it this way. Imagine I make a charge in here. So let's say you could make a sphere and its position could be, let me make it down here. Sorry. If you wanted to do a charge in here, that could, its position could equal the POI. And then let's say Q is an attribute, and we'll say that's 1e negative 6, 1 microcoulomb. And you could say its velocity is an attribute. That's going to be a vector, right? And let's say it's moving at 5, comma 2, comma negative 1. It's moving at some weird ass direction. And let's say its color equals vec, how about 0.8, comma 0, comma 1. So kind of a bluish, reddish purple here. And then let's say its radius, screw it, let's just let it be, oh, actually. So the idea here is the force would be charge dot Q, that's Q. Let me write the force equation just so you know what I'm saying. Remember, we know that force in a magnetic field equals Q V cross B, right? So if I wanted to figure out the force on a charge, it would be charge dot Q times charge dot V, whoops, cross. And this would actually get the, whatever.
Of charge.
Yeah. So what this would do is you could actually now not only generate the magnetic field from the current, but also put a point charge out there and see how it's affected and animate it. And that's kind of the big picture of what I was hoping you might achieve for your oral presentations. Use straight line segments to draw out a shape like a circle or a square or a triangle, and use that to figure out how it affects a moving charge. And here's what's really, really cool about it. If I go to this, whoops, let me get rid of these annotations so I could actually see what I'm doing. Oops. Sorry about that. And sorry about taking so long. I'm trying to go slow, and that way you have time to ask. But take a look at this. Here's the oral presentations. And if you scroll down, there's a bunch of different ideas for things you might do. Try some or all of these, right? So blah, 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 blah. But this is the coolest right here down at the bottom. This is why I thought you might enjoy this. The idea here is this. Think about this. You take that straight wire code and make a circular coil. When you do that, the blue lines represent the magnetic field. And then what you could do is you could put a point charge in there and start it moving, and it should spiral around the magnetic field and bounce back and forth. And this is called a magnetic bottle. And so this is one way to confine a plasma. And if you read about it, you could read about the Van Allen belts. It's really crazy. You guys are actually pretty darn close. You have all the tools from this semester to do this, and it would be kind of neat. Now, if that's too intimidating, there's other options. But if you're feeling really motivated, now think about how tricky this would be. You aren't figuring out the B field at one point in space. You have to figure out the B field each time it moves. So you're going to have to make a loop that inside of a loop, where each time the particle moves, you have to animate the motion. Then inside that loop, you have to recalculate the magnetic field each time, then recalculate the force, then update the momentum, then update the position, then repeat. And it can be done. And it's not that bad. But first you got to figure out, oh my gosh, each time you have to go through the whole loop, and oh my gosh, it's going to be non-trivial to figure out the magnetic field. There's going to be like maybe 3 loops nested or something, right? But it's not too crazy. And if you want, yeah, let's leave it at that. Yeah, so any questions about that? that's the fun part, is getting to do crazy project code and have a good time with it. Sound good? I'm going to go ahead and stop the live.